This is a tutorial for the energy ball simulation on my website. And I actually based this on a simulation by PHET, P-H-E-T. Can't remember what it stands for, but they have a simulation called Energy Skate Park, which is great. And that was the basis of this simulation, but I added a few things that I thought would be helpful. And I've just updated this simulation. So when you start it up, you have this ball on a ramp. The basic idea is to explore conservation of energy, and you can watch the ball go down on the ramp, and you can actually show all sorts of different things with all these things you can vary. One of the things I first show with it is actually Galileo's experiments of rolling the balls down the ramp. So I'll show you how to do that, or at least how I do it. This is a pause button, or if you hold it, it resets the whole track. Now, if I want to show that, I'm going to get rid of the bar graph, which we're going to, there's the bar graph, which we're going to put back in later. These extra things that can go on the track, you can also get rid of them because they make the screen look a little bit cluttered. And I'm going to get rid of bar snap, and I'll explain what that does in a second. And I'm also going to get rid of height. This will actually show the max height that the ball goes up to. So given that, I can now roll the ball down, and that bar will show the height to which it reaches, assuming there's no friction on the track. And you might notice that it actually doesn't get to the exact same height every time, or it may not. And that is an artifact of how I program this simulation, so I cannot get it to be exactly the same every time. And in fact, sometimes it actually even gets a little bit higher if you let time go on. Regardless, if we want to talk about the Galileo experiment, we can reset the whole thing, and we can add a little bit of friction. Now, you can have a coefficient of friction on any sort of hundredth up to 1, and that's what the bar snap does. If you have bar snap on, it only lets you do specific increments. You can see up by 0.05 each. And for the spring constant, you can go up by 10. For the mass, it goes up by 0.5s. For the acceleration of gravity, by 0.5s. Likewise for the speeds. So if you don't want that limit, you can remove bar snap, and you can pick any value of friction. So we could start with 0.25, and you could talk about, I think I've given the ball an initial speed, but you could talk about how, of course, the ball does not roll up and loses energy, and Galileo polished that ramp. And it gets up higher every time, but it still loses energy, and then you could lower the friction to something really quite small, like 0.02. And you could talk about how once he almost perfectly polished it, it got almost up to the same height every time. And of course, you could lower the friction to 0. So the next version, of course, of the Galileo experiment is to extend the ramp. So if you can click and drag anywhere in here and translate the ramps over. And you can just kind of, you can kind of pull this ramp and extend it outwards like that. And then you can add friction back on if you want, but you can just show the kids that it will get up to the same height if there's no friction, even if that ramp is extended. And then so the thought experiment goes, we can now extend the ramp out to infinity. You can't really do that in my simulation, but I'll show you what I would do at this point. Let's let him go up there, and I'll pause it. I'll just make it straight. And if you click on Show H and V, that will actually show the tennis ball's height and speed, and you can talk about how it maintains that. If it's too fast for you, you can slow down the sim speed. You can talk about how it maintains that constant speed of 8.73 or whatever it is when you demonstrate this as it goes. Okay, I'm going to actually just reset the whole thing. So you can adjust the simulation speed as you need. Let's talk about a few other options. So I just talked about how you can show the height and the speed. And you can also show other information about the track, like how high parts of the track are over the ground, as well as the angle of inclination. So you can actually use this to make projectile problems, which I'll show you in a minute. The next way I use this is I'll click on bar graph, and actually I'll get rid of track info for now. And when you move them, you can see there's a total energy of 53 joules, and it shows the transformation between EG and EK. Again, you can slow this down if you would like. You can talk to the kids about why EG never goes down to 0, and you'll see because there's a reference height at the bottom. You can grab it here and pull it up, and then, of course, the EG will go down to 0, and the total energy will be lower. If you want to add in friction, you can watch the total energy drop depending on the amount of friction that you add. Let's reset that. and reset the friction down to 0. I'm going to add a bar snap back. You can add a track snap. What this does, I'll add info back here. It only lets you put things at heights of 0.5 meters from the ground or from the reference height. So it kind of forces everything to be in half-meter intervals in case you want to have a problem where, let's fix this. If you want to have a problem where, the ball is dropped from exactly 3 meters, say, and you can roll it down the ramp. Okay, so that's track snap. I don't usually use that one. Other things you can do is you can combine other pieces of track. You can grab pieces of track from here, and you can connect them. And you can make whatever kind of weird tracks you want, I guess. The kids can kind of have fun with this. It won't really change how the simulation works, and it won't really affect. Paul will never fly off the track unless he flies off the very edge. So the ball will never disconnect from the track, but these are options. If you want to get rid of some of these extra tracks, I'll get rid of track info. If you just click on one of the points and you just put it on another point of the same track, it will just remove that track in case you get too many out of the way. But of course, the easiest way is just to hold reset and get the whole thing reset. There's a couple other things on the track that I added. If you click on spring and loop, it gives you these other options. So if you want to put the loop in, you can just kind of connect it like that. You don't even need to actually connect the loop specifically. And you can change the size of it. It actually doesn't matter if it's not fully connected. The ball will still roll through. And we'll unpause it, and you get a loop, which is kind of nice. So you can have the kids talk about that. Or you can make the loop higher so it doesn't actually make it all the way up the loop, which is fine. It just doesn't fall off the loop. So that's the loop. If you want to get rid of it, just grab it in the middle and drag it back over there. You can see it got stuck in the loop. Isn't that funny? We'll reset the whole thing. You can also scale out, by the way, if you want to make a larger track. But if the scale's wrong, just reset the whole thing. The spring is quite fun. In order to use the spring, it's got to be on a horizontal surface like that, and it will snap to it. And the ball can only roll into the spring from the right side, so you couldn't have the ball go into the spring from the other side. And you can roll him down, and you can see that he will, compress the spring. You can always slow it down if that's happening too fast with the elastic potential energy. Likewise, you could also change the spring constant, so it will compress much more like that, whatever you like. So that's a nice touch with the spring. The other thing you can do with the spring is if you grab the ball and you put it on there, it allows you to compress the spring and then fire it upwards. So you could ask the kids, if we add on, you could ask the kids, for example, given the spring constant and the mass in kilograms, how high up is the ball going to go up the ramp? And then, given the compression, you could fire it. We'll speed this back up again. You could fire it and see how high up they get the ramp. So that gives you that idea. It's a little too fast for me now. There you go. So, it's because the spring constant's so low, it takes forever that spring to decompress. So these are some things you can do. If you want to make like an energy and projectile problem with this, you can add the track info so you can see. We'll put the reference height on the bottom, and maybe I'll get rid of the bar graph for now and get rid of the loop. What you can do is you can see the height of each part of the track here, and you can see the height of the end part of the track and the angle of inclination. So you can compress this guy, and maybe we'll change K, and then fire it off, and then it's kind of a projectile problem. The kids can figure out how far away it should land, and it gives you the answer, 9.76 meters. Likewise, I've also designed it that you can specify how much friction is on each part of the track. So if you add a coefficient of friction here, it will automatically apply it to the track and another track that you add. But you'll see these buttons below. So I could remove friction for the ramp part and keep it on this part. And then you could ask a question like, if I roll him down, how far along the frictiony part is he going to get? So you can roll him down. The kids, you can make this a problem. So he'll stop and it will give you that distance as well. So these are all options. If you wanted to do a horizontally launched projectile, you could do that too. You could make this horizontal and you can give them, you can roll them down a ramp, but you could also even just give it an initial speed. So you could give it a speed of, let's say, 6.5 meters per second and put it on there, and now it's a horizontal projectile problem. They can figure out how far away it's going to land. Let's see, what else have I not showed? Yeah, you can change the acceleration of gravity, so this is kind of fun. You can have the bar graph, and, he's got 50 joules of total energy. How is that energy going to change if I double G, or I guess it was 1.5. So if I double it to 3, you can see that the total energy immediately goes up. It actually scales off the graph. But if you start G at 1, and then you increase it to, let's say, 2, you can see the gravitational potential energy doubles. And if you actually change that while he's rolling, you can make him fly off the track if you like. There you go. Now there's no G. You can also change his mass, so that will also adjust the EG. You can change, as we said, the spring constant and the friction and his initial speed. You can zoom in and out if you want. Let's get rid of some friction. Those are all those options. I made a moon mode. It doesn't really do much. It just kind of looks cool, and the gravity's really low. So I just did that for fun. You can see on the left here, there's like a hot dog stand right there. That doesn't do anything. I don't know why I threw that in there. Let's get off moon mode. Craig mode, it really just shows my face. I just thought that would be fun for my students. So if you want to add that in, that's up to you. And that is my conservation of energy simulation. And yeah, there's a lot you can show with that one. I hope you find it useful.